In this video, we are going to solve some problems based on radioactive emissions. So first, let's look at alpha, beta and gamma emissions. Alpha, if alpha is emitted by a radioactive sample, let's say XZA, then you are going to have alpha, which is helium nucleus He24. So the atomic number Z will reduce by 2 and the mass number will reduce by 4. So this is a general equation. For example, if we have radon 86219, if it releases the alpha particle, so that is He24, the atomic number will become 86 minus 2, which is 84. The mass number will become 215. And then according to periodic table, we can find 84 is polonium. Next, beta. Beta is an electron emitted by a radioactive nucleus. So when beta is emitted, that means we are getting electron, that is E minus 10. And then we can see that the mass number has to remain the same because electron's mass number is 0, whereas the atomic number will increase by 1. We can see an example. Sodium 1124 gives out beta particle. The atomic number increases by 12. The mass number remains the same. 12 is the atomic number for magnesium. Also note that beta particle is released when you have an imbalance of neutrons and protons in the nucleus. So a neutron, when it decays and gives proton and an electron, that electron which is released in this decay process, that is called as beta. So neutron converts or changes into proton and also produces an electron. This electron which is produced in the radioactive nucleus is ejected out with a high speed. That's called as a beta particle. Gamma is released when you have a radioactive nucleus in excited state. That means it has extra lot of energy. So when gamma is released, it is just energy released. There is no change in the atomic number or the mass number. So the asterisk which you see here, it's representing this asterisk is representing extra excess energy. That means it's telling you that XZA here is in excited state. It has a lot of energy. Now let's look at one problem on half-life. At the beginning of an investigation, a sample of the substance emits 3000 particles per minute. So that's at the beginning, that means that is N0. After 6 weeks, that's the time given to us, the count rate decreases to 375 particles per minute. That's N. What is the half-life of the substance? So now half-life formula is T over N, but N, which is number of half-lives, is not given to us, so that we want to calculate. So we'll use another formula, which is N0 over N equal to the power of N. We have N0 and N. We can use it to get the value for number of half-lives, that is equal to 3. Now we can substitute this back into the formula of half-life and we get the answer as 2. Don't forget the unit here, it's not seconds or hours, it's weeks, so we have to write 2 weeks. Now let's look at a problem based on a graph. The figure below shows the count rate from the radioactive specimen as it changes with time. We can see 2000 is the first value at which the sample was, 2000 count rate. That's the count rate, counts per minute. That's the initial value. Then it's asking us, if the count rate falls from 2000 to 500, how much time would it take to decrease from 2000 to 500? So in the graph, we can find 500 for the corresponding time is 8. That means it's 8 hours. Hours, how do I know the unit? I check the graph and I can see the unit written hours. How many half-lives as the number of atoms decrease from 2000 to 500? So we want to find N. We have got the formula N0 over N equal to the power of N. N0 is 2000, N is 500. Substitute that, get the answer as 2. That's the number of half-lives. Calculate the half-life of this nuclide. So we get T half equal T over N. T is 8 hours. That's the time taken to reduce from 2000 to 500. So 8 over 2, that gives us 4 hours.